Let us start lecture number 3 of this module 5. In this last lecture, there was some discrepancy, means I wrote a wrong expression. The delta which we wrote here, that is defined as omega n by omega n, and it is nothing but your omega divided by omega n minus 1, and I wrote basically omega n is equal to L upon C, which is incorrect. Nobody noticed it. This is wrong. It should be your 1 over Lg. It was there, but later I think here if you check your copy, it was we were getting somewhere minus C, so it should not happen. So, what we are going to here omega Lc minus 1, here I think at this point I wrote L by C. So, that should not be there, and here if they are going to change here, that we can write here del F by F plus here half delta L by L delta C by C. So, expression was same, only here I think just I put under root L by C, and that was wrong. Now, today I am going to discuss basically here the minimum cost tuned filter. We saw this tuned filter design. Here now we have to see the minimum cost, because the cost of the filter should not be more than 5 to 15% of the total terminal cost. We will prove that the cost of filter, if we are taking k, that is a summation of the two, that is the one is the linear quantity which is varying with the size, and size is just we are defining the size is in terms of MVAR, and MVAR is basically defined in terms of the capacitor value. So, this is I will prove it also, this expression will derive. So, here you can say if the fundamental component here, the size of here is increasing, the cost of filter is increasing. But if you will see the harmonics component, if this size is increasing, then the cost is decreasing. Means if you are adding both together, we are having this curve almost. Means at any particular point you will find the minimum value for which the cost will be the optimal for the given size. So, we will see that how we are going to get this A and B value, how we are going to calculate this. Before deriving, these are the few points that should be considered. The filter capacitor is subjected to the current and the voltage of two frequencies. As we are talking here, a filter, that is a resistance, that is your R, here C, and then we are having inductance, it is we are talking here the shunt filter. So, we are having here capacitance, here inductance. So, in this branch, no doubt we are having so many currents, because this voltage is there, harmonics currents are there, but this filter is fundamentally here your the fundamental component is there, and then we are having that is one, and then another is corresponding to H component. Now, no doubt other component will be also there, because this resistance and capacitance will form some impedance for other currents as well, but this will be the significant, this will be more significant, because this is designed, it will be tuned here, only R will be there, but other components will be there, and for the other components this will offer huge impedance, and finally, it will be not there, that contribution will be very, very less. So, that is why it is said the capacitor here, it is basically sustained for the two frequencies. One is here your F1, that is a fundamental component, and another is a harmonics component for which it is tuned, it is designed, and that is your FH. So, you are nothing but FH, it is your H, that component here, that is F1. Similarly, it is true for inductance as well, it is inductance, it is true for the resistance as well. The rating of capacitor now, it is defined, it is not in terms of C value, it is not in terms of farad, we rate this in terms of MVAR. So, the rating of the capacitor in MVAR must be the largest sum of the fundamental component reactive power, because it is MVAR we are defining. So, the two frequencies components are there. So, this is the fundamental components reactive power plus the harmonics components reactive power must be added. So, that is the rating in MVAR, the power reactive power it is giving. So, the cost of the here the capacitor is directly proportional to its rating, means if rating is increasing, the cost will increase, that is obvious. The size of capacitor by definition is the reactive power of the capacitor at the fundamental component here. What we do, we say it is a 10 MVAR capacitor, means that how much reactive power it is giving at the fundamental component. we never count this, because at fundamental reactive power we are other frequency we are not considering, because this filter should also provide the reactive power support at the fundamental frequency. So, the rating here we are defining the reactive power based on this, that is defined as S in that expression. So, it is only we are taking the fundamental component in terms of size of the capacitor. However, here the rating here we are adding together. Now, the fundamental frequency source is essentially a constant voltage source, because whatever it is connected here we are having this V1, but the harmonics component is the current, it is not voltage. AC side we are having harmonics, what I said, this is your H, that is NP plus minus 1, it is AC side current harmonics, it is not voltage. However, the DC side we are getting the voltage harmonics and there is no current harmonics. So, this harmonics component, that is why it is written essentially here the fundamental component is a constant voltage source, here the balance V1, that is a supply voltage balance one, and your the harmonics source is nothing but a current, that is normally it is an IHF. Why IHF? Because it is a harmonics, the particular harmonics current which is flowing. So, this is it is a defined, that is a current which is coming. So, based on these two criteria, voltage and frequency, now I will come to here, you will see the rating of a capacitor. Size of the capacitor is S, mind it, rating is the total sum of the reactive power supplied by the capacitor at the fundamental component plus the reactive power supplied by a harmonics component, that is why here HF is there. So, you know this is here V1 is the fundamental component and this is your omega 1 C, here this value is there. So, now this is denoted at the S, that is a size, that is in MVAR. So, this is here replaced by S. Whole this equation, this also we want to write now in terms of S, because in the previous the first graph I showed, it was in terms of size and the cost. So, this is your S per phase and here it is your cost, whatever the monetary value you are using, and one was going like this, another was going like here, means your minimum total will be somewhere at some value somewhere. So, this is your size, this is the rating. So, total fundamental component, here this component, this is nothing but you can see I square into XC. XC is your for this component here it is H omega 1 C, H already here is there. So, this is your harmonics component reactive power. Now, this component can be changed to this one if you are multiplying here V1 square, here V1 square, the V1 square omega 1 and C is your F. So, H is there and V1 square is up. We want to express this because the V1 is your, you know it very well, this current also you know, because once you are analyzing the frequency components of any HF harmonics, you can know what will be the current. This current, this one, it is nothing but it is your I1 by H ideally, when there is no overlap. We defined this already, but if there will be some overlap, some factor here will be coming into your picture. It will try to reduce some component, already we summarize that your overlap etc. will try to reduce the magnitudes. But this value is very small, we can even though sometimes directly take this peak value and we can just work if U is very small. So, this is your QRC, means reactive power supplied by the capacitor. Similarly, to have the rating of inductor will be, now I can write in this fashion. Now, how I can write this? This is the final expression. We know this is, I can write here QRL now, the fundamental component, I can write here it is your I1 square omega 1 L. Because the current which will be flowing here inductor, so reactive power loss here it will be this value plus whatever this current that is flowing HF square into omega 1 into here it will be H, because this XL here for that that component. So, here omega h will be there. Now, we want to replace the L, we do not want the L at all. We know there is some relation, and also we know this value, your S, it is your nothing but your V 1 square omega 1 c, or I can write this in terms of I 1. I can write here this is I 1 square, this x c your omega 1 into c. Now, we want to replace here this L, and we know this your omega n, it is your under root L c, means I can square it here. So, this is a square here L c 1 upon, right, sorry, is 1 upon, yeah, you just correct me, it is L c. So, means your L is 1 over omega n square into c, or I can say here is h omega 1 c. I can write this, and then we can put this value here L, means we are getting your I 1 square omega 1 into here 1 divided by h square omega 1 square into c. Here I can write your hf square h omega 1, here also I want to replace this. So, your h square omega 1 square here c, then we can cancel it, means this is a cancelled by this one. Here your I 1 square into omega 1 c into 1 upon h square, plus here this is also cancelled with this, and this is the similar to this component of the first component here, this component. And it is also valid because the reactive power supplied at the resonance by the two will be equal, because you know omega L here will be equal to 1 upon omega c, means x L is equal to x c. So, whatever it will give, it will be equal to that point at the harmonic components. Whatever it is giving, it will be for the inductor as well at that particular harmonic. So, this value is now your S. So, I can write S upon h square plus here V 1 I h f square h into S. This value we are getting the same value here. So, this expression is written. Now, we can conclude. You can see this component at the fundamental component, the reactive power consumption, if it is designed for the tuned filters for any hth harmonic, here this is giving S. So, this is going to give a less amount, this H, it is a fifth harmonic, means reactive power it is generating, reactive power absorption it is up that value. So, that is why if it is designed for any, let us suppose fifth or seventh harmonics, the reactive power generation is more compared to its absorption, and that is why it works as a completely as a capacitor in terms of your fundamental component. So, here and that is h square means huge amount, it is varying. So, this is your QRL, that is the rating of inductor is defined. This is one way to define in terms of reactive power output. So, from these two expressions, if the unit cost of the inductor is defined, that is here I can say $ per MVAR for the capacitor, that is it is UC, here it is the unit cost of capacitor, means it is the $ per MVAR, here we are talking MVAR, and UL is your unit cost for your inductors, means that is a $ per MVAR reactive power support by this one, then your total cost will be this, subjected to if you are ignoring this cost. This cost of course is very, very small compared to these two costs, it is no doubt about it, because the resistor cost is very, very small. And in the tuning basically this is independent on the tuning frequency, because these two are the varies to tune this. This is only how much energy it is going to dissipate it and how much damping it is providing basically for the transient disturbance. So, your K will be this one. So, from this you can just put this value together for your, here you can put the value for this from here and you can put this value from here, you will find this expression here, just it is put it here and now you can combine together. And finally, you can see we are getting the similar expression which we derive in the beginning here, this expression, this curve, because the fundamental component which was rising here, that is A s, and your B upon S, it is your the harmonics component. So, one is decreasing and another is increasing, means we will get some optimal value somewhere at particular size, the cost will be the minimum. So, we have to find what will be this minimum value, and it is obvious that you can differentiate this k with respect to S and equate it 0, you will get the value of S, optimal value of S, and then finally, you can get the k minimum for that value, you can put it there. So, here it is basically differentiated with us. So, your this component, if you are differentiating with respect to it, then it becomes only A, and if you are differentiating this, you are going to get B upon S square, and if you are equating 0, you are getting this S here, that is optimal value here, you are getting B upon 8 under root. And if you are putting this value in the equation here, you can put this value in this equation, you are going to get this k minimum value, that is the cost will be under root 2 A B. So, this is basically the optimal design of the capacitor. So, basically based on your A and V values, these values are calculated, these values are basically defined, you can say what is the A? A is basically the unit cost of the capacitor and inductor in terms of some harmonics components are arising. Here also you can say the B component, this is S is down here and this is the V1, this is a supplied voltage, this harmonics current, what is the magnitude of this, and these costs and H component is coming into the P. So, these values are known to you, this cost is, you know, the what is the cost of inductor, what is the cost of capacitor in terms of MVR per unit. Harmonics component you know, for which this is a tuned filter, and V1 is your supply voltage, that is given the fundamental supply voltage, and IHF is the current, just you have to calculate based on the fundamental component. For example, let us see one example how to calculate this. Let us suppose you have been given one example here, just I can take it, that is it is said that is a plus minus 300 kV bipolar system is there and it is consisting of 4 bridges. So, it is the 4 bridge of 12 pulse converters. Then we have to see 12 pulse means here the 4 bridge means it is a one bridge here, here one bridge, then it is simply you can say it is your transformer here, that is your star star, here another transformer, this is your star delta. So, 2 bridges basically forming 12 pulse. Then remaining here it is forming your negative side of this. So, these are the 4 bridges, means it is having completely 4 bridges one side. It is not said the 4 bridge per pole, it is said 4 bridges in total. So, the 4 bridge here means the 2 bridge per pole, this is your DC here it is going, and this side also we are having. Now, in this what we have to do, what is the voltage across this? We require the fundamental component that is coming here, the VF. So, the AC side voltage is given to you, this is AC side voltage is given 235 kV, this is line to line voltage. So, here this minded, the expression that we used here, this the V1 is the phase voltage, because we are talking whole calculation the per phase. The cost here is the per phase, not for the total. So, here the whatever it is given by under root 3 will be there. Now, you can calculate the current also. Here this total power is given of this link. Total power it is given, it is your, the current is given 1 kilo ampere. Now, you can calculate the power, because this is 300, this is 300. So, it is 600 voltage multiplied by this power basically is coming here, divide by 4 means all are sharing the same power. So, power you can get from this side IL1. means this is your AC voltage. This total power means PDC. It is your 600 multiplied by 1. This is in kV, this is in kV. So, we are having 600 megawatt. Now, the 600 divided by 4, it will be the power coming in 1. And then you can require this PAC here in terms of power factor, you can calculate, and the power factor is also given here for this. The power factor is given 2.886. Means for this it is given power factor is this value is already given to you. So, what happens, just you can say this is a DC power, this is your 600, I can say this is your under root 3, this is your V1 into your I, we want to calculate this IL here, IL1 into cos phi. Here what we can do, if we are taking the V1 as a per phase, then it will be 3 times. If you are taking line to line, if you are taking this value directly, what happens, only just you are getting confused, if it is nothing said, it is always line to line. And whatever this expression we are using the per phase value. So, if you are taking this here V1 in that V, then it will be 3 times here. So, what we can do, we can, and this will be your equal to your PDC. So, this is your 600 megawatt. Again, always you should be very careful about the megawatt, means now this should be in kilo, this should be in kilo. Then kilo will be megawatt, and we are not going to here multiply it by 10 power 6. Otherwise, we have to put here 10 power 6, you have to put here 10 power plus 3, and here also the same value you can get it. So, this is equal to your 3, here 235 divided by under root 3, this is a kV, and into your IL1, and your cos phi is given 0.886. Now, this will be by 4, of course, because if you are talking only current here, the total current you are going to divide by 4. So, it will be this here, the AC will be multiplied by here divided by, no, this total power will be total AC, but this current which is we are taking, now it should be multiplied by 4 here. So, this current is one current we are taking here. So, this will be basically multiplied by your 4. Yeah, same here, divide by 4, of course. So, your IL1 will be your 1700 by 4 ampere. This will come this value. Okay. Now, this is your RMS value. There also H1F we are using the RMS value, because in reactive power this value is not peak value here. This value is the RMS value, is not the peak value we are talking, it is RMS value. Here also this is RMS value. So, there is no peak value concept here. So, whatever if you are analyzing the Fourier series, you are getting the cosine and sine component, those are the peak values. The components, that is A and Bx components are the peak values are coming. So, you have to convert back to again back to your RMS value. But here already this value is your RMS value. This is RMS value, because this is RMS, the RMS, everything is RMS. So, it is RMS value. Now, I want to calculate what will be your HF, it is asked for your fifth harmonics. So, H is 5. So, it is your IL1 divided by 5, and the total value it is coming to be 85 ampere, because this divide by again further 5. So, that will be 85. Okay. Now, if you consider the factors of your U and the delay angle, as I said, some factor is going to multiply it by some k factor. Since we did not analyze for how to calculate this k factor, we are not going in the detail also, because otherwise for the different U and alpha you will get the different factors, again it is a very difficult to calculate. So, if it is given this factor, then you should multiply that factor. If it is not given, take as a unity, means that is ideal, means U is 0, means it is nothing said. Then put this value there. For other here calculation of the cost, you require UL, you require UC. You can see in this expression, now we have the H value, now we have this value. This value is 235 kV divided by under root 3. You have this value, only we require these two values. This is given to you what is the cost, and the cost in this example, it is given, this is your cost of capacitor, it is given $3.5 per kVAR, and this value is given $8 per kVAR. Okay. So, here if you are multiplying this value now S, if you are not changing in the MVAR, this your cost will be even in the kVAR. Means how you are taking, this is the S value if you are taking here, this your values are, if you are taking in the K here, K etc., then you have to go in the kVAR. Otherwise, this kVAR you have to convert in the MVAR. Then you can put directly, no problem. So, what happens if you are going to put this value, your A value we can take here, this A value, it is UC, here it is the 3.5 plus your UL, that is 8 by 5 square. Here this will be basically coming 3.82 basically dollar per kVAR. So, here A we are using in the per kVAR. Now, size you are going to use in the kVAR also. Okay. So, here this value which you are going to use, it is should be also in the kVAR. It is not in MVAR. If you are using this K, so this will be in A. If you are using here K and K, then it is becomes MVAR, mind it. So, we can go for your B value, or you can simply, because we are taking in the MVAR here, you just simply convert this value, what must be per MVAR?
Into 10 power 3.
Yeah, into the 10 power 3. So, it is your $3820. Because here again create confusion. So, always if it is defined and derived in the same unit, convert in the beginning itself. So, here will be your 3820. Now, your B value here, this will be, we can take from here the V value, V is your V1 square into your IHF square UC plus UL divided by your H. Okay. Now, this value we can put, yeah, 235 by root 3 of square into your IHF. If you can take 85, you can take, otherwise factor. So, it can take 85. So, it is 85 into, why I am writing minus 3? Because I am making in kilo. So, this kilo now it becomes MVA. Into, this should be added together in the per MVAR. So, it is your 300 plus 800 divided by 5. What I did here, 3.5 this value means 3500 per MVAR, this is 8000 per MVAR. We put it here because everything now it is in MVAR. So, this value is not in MVAR, but actually into MVAR, because already it is a B by S. So, it is in dollar. So, this value is going to be divided. So, into a MVAR here, means dollar MVAR I can say. A was the dollar per MVAR, here this is dollar MVAR because divided by S here. And this value if you calculate, you are going to get something. Basically, we require here for the minimum value of the size of the S can be determined, just put A and B, you will get this value. Now, it is in MVAR, because this is also in the here, this is the per MVR, it is here into the dollar MVR. So, this is going up back and a square root means we are getting in MVAR. So, S value is coming around 9.32 MVR per phase. This calculation whole is for one phase. So, if you are having 3 phases means you require the 3 different tuned filters for the different phases. Then you can again put this value, you can get the cost, what will be the total cost, and the cost is approximately coming to be the 71,000 US dollar per phase. So, that similarly you can calculate. So, this is one illustrative problem how to calculate. Basic problem only happens, this formula etc. is very simple, only here you have to mind about your unit conversion, here you have to be careful about your the bridges etc. Because here how the bridges are formed, once this picture is clear then you can calculate it. Once it is not clear, once here simply your IL is not coming correct, everything is wrong. So, this is your one of the illustrative problem that I just tried to explain. Now, we have to go for here the design of high pass filters. So, till now we just saw your tuned filters, but for other harmonics component if they are significant, we normally use the band pass filters, so that the filters of particular harmonics onwards should not enter into the AC system. Whatever characteristic or uncharacteristic harmonics are there, we have to take care. So, normally you can see this filters here, the diagram, this is A, it is basically first order filter. In the first order filter, it is nothing but RC filter, we call, you know, the band pass filters are simple band pass filter is RC filter, and here you can see this capacitor, here is only one capacitor is there, which is large capacitor is required to sustain this voltage. And thereby what happens, this is a very lossy and it is normally not used. So, we go for this higher order band pass filters, and the B is your second order, here it is your third order. You can say if you are keep on adding the elements, the order is keep on increasing. Means you have to make a combination of LC. If you are having 1 C RL, it is the first order. If you are having 1 L 1 C, it is second order. Now, you are adding here the 2 C 1 L means is a third order. So, normally second and third order band pass filters are preferred, and now you can say based on its impedance here, the RLC here, we can write the impedances here. Impedance here, it is this 1 over j omega c plus the parallel combination of this, which is written 1 upon R plus 1 upon j omega L, inverse of this is added. Similarly, here now we are having this series with the parallel of this L, this series now parallel of L, and then C is here, it is added. Here only the mistake I have done here, the C1 and C2 are there. So, both C are written here. So, I can say it is your C1, here it is your C2. In this case, it is a simple C. So, this is your impedance. Now, our idea is not to know only the impedance, because these impedances RLC are designed in a such a fashion, so that we can know what is the quality of this, and then we can tune so that we can have a very good characteristic. And the characteristic here, now you can see for the second order onwards, here you can see this is your characteristic. For the varying value of your quality factor, you can say if your quality factor is increasing, now just see it is going to be a tuned filter. Q just increasing, you can see now here the Q is very less, now it is just coming here, it is just flat. We require this is a component where this should be passed and this is blocked. Again, how you are designing means it is providing the minimum impedance for higher order, high impedance for the low order, means it will only allow to pass the higher order onwards. So, once you are increasing here, you can see this quality factor, this component is keep on rising, and normally it is becomes a tuned filter. So, we will see how these expressions are drawn, means we can derive expression here in terms of frequency and also in terms of impedance, like we draw for our tuned filters here, and the final expression will come here. So, let us here derive this expression, so that we can know how this Q is going to affect your this impedance. This impedance basically written as Z2 prime. Prime means we are just dividing by x naught. X naught is nothing but in terms of L and C. Here, if you remember earlier we defined here your L upon C. We can have the omega n, it is defined over 1 over L C. Whatever the value of this, there will be some tuned frequency omega n for given L and C values. So, this is defined in this term, and we can write this quality factor in terms of x naught. What will be this value? R by x naught or x naught by R? It will be x naught by R. Right. So, I want to go back the impedance which I wrote here. So, Z second means I can write Z second, it is your, I wrote it is 1 over j omega c plus here 1 over r plus 1 over j omega l, here it is inverse. Here this z, the prime we are going to get z upon x naught value, means we are talking the per unit value. So, and another term here f naught prime, it is your f upon f n, or I can say omega upon omega n. Okay. Now, here see this value we want to, let us multiply and divide here. I think this, can you remember this value is correct? Is correct. So, here I can just multiply here x naught here in whole, and then I can divide. So, it is 1 over j omega x naught c. I just multiplied and divide here. So, it is cancelled out here, plus here I can write x naught by r, because this is the inverse, mind it. So, here if outside if multiplied here divide by here means it will go up here, plus your x naught by j omega l, the inverse. I can write this. Now, see what is this? This value x naught c, this is x naught, it is your under root L upon c, yeah, it will be omega n, 1 by omega n. So, what happens this, it is your x naught 1 over j omega divided by omega n. Now, I should be very careful because last time you did not notice and I did some mistake. So, here it will be omega n, now plus this value, it is q, now what will be this value? It will be your 1 over j omega divided by omega n. I think this will be also the same. Because this is similar fashion, here it was combined together, here is omega l upon this. And this we are going to have, this is x naught 1 over j f prime as per our definition here, plus here q plus here j f prime here, that is the inverse. So, basically here this is a complete bracket. Now, this will be divided this side. So, we are going to, if we remove this, we are going to have z second prime. But I think our expression is coming something here 1 upon q should be there. The final expression, I think, why it is so? So, this q is, that is why I am just doubt here. your this is x naught. If you will see just the last term, what we got? This it was your under root L upon C, then it is I can say omega n L upon R. So, this is your nothing but under root L 1 upon L C, sorry. So, this is going to come, this omega n is 1 over under root L C into L divided by R, means it is your L upon C divided by R, means x naught upon R. No, it is correct. This is correct. It is correct. It means the expression which I wrote is not correct. So, here this is your Q. It is not 1 upon Q, it is Q. So, we are doing the correct. So, there is no problem. But here since this value is coming 1 upon Q, but it will be always inversely proportional. It will come because already this inverse is there. So, if you keep on changing this value, this magnitude here will vary in this fashion. Similarly, we can derive here for this whole this scenario we can get in this form. What happens? You can say this is j omega c 1, here your L part, here another C part 1 upon F is coming, here this is coming 1 upon this, it is true. And you can see here it is having the different scenario. If we are changing Q, it is going very fast. Here you can say 0.77 it is this, and we are having since second order. So, there is one here, the peak will be keep on coming, is a third order because 2 C and 1 L is there. So, normally the second order filters are very prominent because it gives complete bypass, because you saw this previous figure, it is a very perfect compared to this. Here you can see this is just like here a straight line if you are having low quality. So, whatever the frequency component F here, beyond that you can just pass it, means it will provide the minimum impedance for higher component here, and this E it is nothing but your F upon Fn, this is F prime. So, this is the basically the band pass filters. Now, we have to see another aspect of this, that is, you know, this is the case when the filters are there, there is no parallel impedance, etc. This is analyzed in isolation, but it is not so. Because we are having the filter impedance, we have the network impedance as well, and then we are our harmonics current generation. This is basically converter which generate your the harmonics component, and that is a current source, it is not a voltage source, means the harmonics currents are generated. So, this current which is flowing, now it is going to be through this filter and through the network. This is a AC network. While analyzing all this, we assume this side we do not have anything here. So, everything is going through this, but it is not so, because your network is having some impedance, and that is it is called, if this impedance is called your the network impedance at the fundamental component. So, ZHN here, this impedance of network harmonics of hth order. No doubt this impedance here, the network impedance is having the impedance for the fundamental component, this is the AC, and that is required because this should be there, the network, the fundamental component. But it will also offer some impedance for your harmonics order. If it is designed for fifth, so for fifth, if you will see at the filter terminal, it will be having some impedance. So, this Hn here it is written means for order H impedance. Fundamental is there, which is hardly matter, we want this fundamental component should go there or should come from the network, hardly matter. But this filter which is designed for hth harmonics, so this current which is flowing here, remaining it is going to the network. If this network is offering the infinite impedance, then total current will come here, means this is an open circuit, but it is not possible. Another option, that if it is offering the short circuit, means 0 minimum impedance, then the filter is having no use, because the total current will pass here. Whatever the filter you are designing, it has no meaning, because that current will go to the network as well. So, that is why here it is written, if the impedance of the filter is your HF, this is your HF, and this is your HN impedance. So, this current which is flowing here, that is your harmonics component of any harmonics component, it is divided into the two part, one is through the filter, another through your network. No doubt we are devising the here network that it should provide the minimum impedance. One option, the minimum impedance here, if going for the tuned filter, here let us suppose you are having, this is your resistance, this is your inductance, this is your capacitance here. If this R is 0, this is a short circuit at the that HF, means your here this is HF, here it is 0 if R is 0, because this we are talking the impedance of this filter at the Hth harmonics for which it is designed. So, this will be 0 if R is 0, but we never keep 0 because we want some energy should be dissipated that harmonic component and also some damping, otherwise there is some oscillation here. The sustained oscillation will be there, energy charge and discharge. So, that may create problems. So, we should have some circuit here, some resistance R, and once you are putting R here, now it may be comparable to your network impedance. So, that is why here the voltage, that is we can write whatever the component here there, we can calculate this, what will be this voltage. Now, what will be the component? Now, this is nothing but your VH, I can write here, it is your IHN into your ZHN. Can I write this voltage? Whatever this current multiplied by its impedance for that harmonics component. So, here I have written. Now, your this HN in terms of IC will be your, I can say IH, basically all this H it is looking like N. This H we are talking here, actually this is slightly this H and R here, this is H N and here it is H N, here it is basically changed here H N, here it is H F, here it is H F. H means a particular harmonics order, F for filter, N for network. So, here just why here this HF is written, HF means for filter and Hth harmonics. Similarly, the network here, this is your for that harmonics. So, then it is required that we should write here. So, from this figure we can write simply, if it is your VH, it is nothing but it is your IHN into your ZHN. Here is the network of that component, and this value we can write this IHC into what will be the current here. This current, it will be in this current, the impedance which is multiplied by the current we want, this current means this impedance multiplied divided by the total impedance. It's true. So, here we can write this ZHF divided by your ZHN into ZHF into, I can write ZHN, which is written here in this expression. R in terms of admittances, we can just divide here, we can write in this fashion. Now, you can see what will be the voltage and what is the impact here. As I said, if Hn is, there is a possibility that your network impedance is 0 for that harmonics component. Although it is unrealistic, but it means that it is the filter is of no use and whole current, the harmonics current is going through your network rather than filter. So, whatever you are designing filter has no meaning, but it is no doubt it is unrealistic. So, it is your filter, I can say filter effect is nil. Another here, this Hn, this network one, that is infinite. Now, it is a behaving open circuit, whatever this is, now it is the pure condition when the harmonics generated is passing through the filter, it is not going to the network, and this we require this condition. If this is there, it is basically the ideal condition, I can say. But it is not possible, neither we can have the infinite nor we can have 0, means it is in between, and therefore, the network basically and filters are in parallel, and sometimes they may form the resonance. And even though if it is forming resonance in the network, here this is your source converter, this is your filter, this is your network. This is, I can say, network, this is your filter, this is your, I can say, source of harmonics. So, there is a possibility here if impedances are resonating each other, then huge voltage arises across this, and that is also not desirable. But in the most cases what we want, that your ZHN should be large enough than your HF. Means that is the case when we are having this condition. So, that it should not enter to the network and it should go down one. So, we design the filter to make this, what we do, this one it is in our control, this is not in our control, because the network as a whole you cannot control. This component you can have, and here you have the parameters. So, the option here that you have to decide the impedance for that one. For the impedance, you know, this is already at that frequency, it is 0 at the tune frequency, these are the impedance here 0, only this is contributing, you make as minimum as possible. But at the same time you have to see there should not be any resonance, and also this should have a should not have a the oscillation circuit, it should have the properly damped. So, this is basically impact of your network on your the filter design. So, whether you are going for the tune filter or whether you are going for band pass filter, these impact will be always there. So, with this I can end this lecture of your filter design, and the harmonic analysis part is over. Next we will see the grounding and your DC line in this one, and then this module will be over. Thank you.